Okay. So exam 2 is coming up. So as mentioned before the break, so again, Thursday we will have the exam. It will be very similar format style to exam 1. Meet in the Ingman lab. You'll be able to take it on the computers there. If you want to bring your own computer, you can take it on your own computer. The same style as what we had before. Is there any questions about how it's going to be taken? Okay, so exam 2 on Thursday. Ingman lab, so make sure you do go to the right location. Ingman lab. And that is upstairs in Web 210. I apologize for having to cancel office hours today. So I've opened up, I just sent an announcement on my way here. I'll have an extra hour tomorrow in addition to Thursday. So tomorrow will be 12 to 1. So extra hour, extra office hour. Wednesday, 12 to 1. So if you want to ask any questions at that point, I will be in my office during that time, and then I'll be again on my office hours on Thursday. Okay, so topics, there's going to be 3 main topics: identifying op-amp configurations, analyzing op-amp circuits, and then determining solutions for a forced order linear circuit containing either a capacitor or an inductor, but not both. So it will only be a first order. Okay. Any questions about the content that will be on the exam? No questions? Okay. Hopefully that will be straightforward. Unit 2 practice exam, or practice problems. So they should have all of the solutions for those if you want to use those to help you study practice problems for the exam on Thursday. That will be a representation of the work you guys have already done, along with some new ones, hopefully. All right, so I had a request to go over 2 types of problems last time, mostly to focus on this review for op-amp identification and then solving multi-staged op-amps. So I put together these notes for that. By the way, these notes were uploaded to lecture 14, if some of you have your computers and want to make sure to access those now. All right, so the first thing is identifying op-amp circuits. So how do you know which configuration you have? So you have to look at the input source is the main part. So first look at input, and then see if there's feedback or no feedback. I'm just going to do feedback. And with that input or inputs, so input or inputs are going to make a difference on which configuration you're going to have. Feedback, and then 3 is you're going to narrow select or narrow options. And then on this one, it depends on pathway from input to the op-amp. Okay, so for this one, for example, my input is here. So I then decide, yes.
Oh, never mind.
Okay. I can see here now, like usually I'm like, please let me know though. If you can't see it, please do let me know because I don't always catch that. Okay, so looking at input, I see where the input is. This is my input into it. Then I need to see, is there feedback or no feedback? This is determining like, yes, there is a pathway from the output back to one of the inputs, which is the plus or minus side of this. So these two are my input locations. If I have little wires here and I have feedback going to them, that's not considered feedback. That's into the sources, so that is not part of the feedback, okay? So I know in some of those more complicated circuits, some of you guys were getting confused by that part. Okay. Okay, so feedback or no feedback, does this one have feedback? Yes. So then I see again, how many sources do I have? In this case, 1. So it's going to have 3 options if I have just one input source. Non-inverting amp, inverting amp, and voltage follower. So with feedback, those are the 3 options. So when I say I narrow options, that's what I mean, is that you can only have those 3 type of configurations for a 1 input source. So then I look at the pathway and I see that this pathway goes from the source into this on the positive terminal of that. That's going to help me identify that this will be non-inverting amplifier. Does that make sense? Some yeses. Okay. All right, next one, source. I do have a pathway back from there into the input. And so it does have feedback. And then that feedback in that pathway goes from the source here into the negative. So it's going to be inverting amplifier. So negative for inverting, positive is non-inverting. All right, this one, I have 1, 2, 3 inputs. So with more than 1 input, I have 3 options: inverting summer, non-inverting summer, and subtraction or difference amplifier. So again, each time, however many inputs is going to determine how I narrow it down. Do I have feedback or not feedback? So looking at that, I have a pathway to my input and to the op amp. So yes, it has feedback. The pathway from these sources into this, I'll go through into the negative. So this will be an inverting summer because it goes into the negative terminal. Okay. All right, this one, I have 1, 2 inputs. And on this side, I do see that I have a pathway, highlighter, that goes into the negative terminal. So feedback is there. I have 2 inputs, so what are my options? 3 options. Say them to yourself for a second. 3 options are, okay, inverting summer, non-inverting summer, and difference or subtraction, okay? All right, with 2 of them, and I see that 1 pathway goes into the negative side, 1 pathway goes into the positive side, so I have 2 that are different. That's what's going to determine that it's a difference or subtracting amplifier. So having them on 2 different input sides, that's what gives you the difference. Okay. On this one, this will be my source and this will be my source. And I do have feedback here. And so 2 sources with feedback. What are my 3 options? Perfect. Inverting summer, non-inverting summer, difference amplifier. That's always what you can say to yourself. Okay, then look at the pathway of where these go. So this pathway goes combined into the plus side, so a non-inverting summer. Okay, that was the easy part. Now you get the little bit harder part. What if the circuit looks more complicated? So then you have to identify the parts of that. So in these that have multiple like stages, you have to say, well, where is the first, like where is the pathway to go into the op amp? So hopefully you see from here, like there's no like external input onto that side. So you would say like, okay, that's not the pathway. So the pathway must be coming kind of from this side into that positive terminal. Okay, because that's kind of where the left side's kind of going into there. So this is where you would identify like this is where my input is. And then what do I ask next?
Where the voltage is going into.
Okay, so I could ask that one. But feedback or no feedback? So does this have feedback or no feedback? Okay, why are you saying no feedback? Okay, here's the output.
I just looked at it wrong, my bad.
Okay, but do you see that? So
Yeah.
looking at where the output is and highlighting where the connections, and does it connect back into the input? And there would be a connection there. So it would have feedback. So to determine feedback, start at the output and then kind of highlight it back to the beginning through elements, if there's elements. So voltage follower doesn't have anything there. Or it just has one resistor through there, and it doesn't have a resistor that goes to a ground. Okay, so into the positive terminal, feedback, what is this one? Correct, it's non-inverting. Okay. What if I see something like this that has a capacitor in it, and we haven't even learned about capacitors? This would be none of the above, okay? Because this is not one that I'd be able to identify as being similar to anything else. Yes?
Are we expected to identify switch and comparators?
Yes. Okay. Okay, let's look at this one. I'll put it kind of over here because there's lots of kind of components to that. So take a minute. See if I got this set up. You can use the QR code to see if, need to make that a little bit bigger. What do you think this one is? Great. Make that a little bit bigger so you can see them. Okay, so it is a comparator. So in this switch comparator would be the same. So this is a little confusing because you have a wire that kind of comes down. It looks like it might kind of feed back into, you know, kind of some of these. But that's a power supply wire. So anything else that's not at the input terminals and that wire out is going to denote it's going to be power. So even though there is some feedback from the power wire, it is not going to be the follower because it's not from the output back in. So the output pathways go here into there, and that's the only connections at the output. So no feedback. So this is correct that you put a switch comparator. So either one of those would be a correct answer. Okay, questions on this? Yes.
It's like the only reason it's a switch is because there's no feedback, or is there like any other part?
Correct.
Okay.
So if it's no feedback, it can only be a switch or comparator.
Oh, okay.
All right. So with feedback, you have to have feedback in order to have a voltage follower. Oh, didn't want to move that. Otherwise, if there's no feedback, it's just a switch or comparator.
Okay. And I guess there can be like input from 2 voltage sources in a switch.
Correct. So you can have both inputs. So in this case, you have kind of some inputs coming to both sides. In this case, you have it going through, what is this? You guys have seen this before.
So,
It's a whetstone bridge. So this is having input going from both sides. And then this is where the other parts of the input are coming. So the whetstone bridge that you guys saw had ground on one side and then like a voltage source on the other, and then it had the dividers. And this is a little different in that the whole feedback is actually coming back through to provide you a source on one side and a different source on the other. Yes.
So as a whole, the circuit, what really is it? Do you know? Like,
I don't remember. I do not remember what this one is. Let's see if it has a sensor in there. Let's see. Yeah, I don't see where the sensor part's coming in. I think it might be the thermistors, the VT1 and the VT2. So I think they're probably phototransistors in there. And so it might be part of a camera system, but that's just a wild guess. I don't remember which one specifically that one was for. Okay, here is a low noise amplifier for biomedical applications. So identifying what is this one? Or maybe I'll just put a star by it. This amplifier here, what configuration? Sorry, it's not letting me duplicate. Here we go. There we go. Okay, correct. I think everybody's getting that one. So this would be a switch comparator. Okay. Let's do. Okay, let's do this one. So this amplifier here. Yeah, I'll hide them for a second. All right, determine what that one is. Robo-B. Oh, shoot. Okay. Is that? All right. Very, very interesting. Not a Robo-B. So this one is a follower. So this one's harder to say, where is my input coming from? So I'm going to skip that for the first part, then determine, does it have feedback? As I look here, like this kind of goes off somewhere over there, but then I have this connection, again, it kind of goes off somewhere there, but then it's connected back to the input there. So it does have feedback. So I didn't see anybody put switch or follower, or I mean switch or comparator, which is good. So identified that it had feedback. I don't have anything, I mean, I have some wires connected to that, but with it connected directly to the output, then that wouldn't be like an input coming in from either side. So in order for it to be considered kind of an input from either side, I would need some resistance. Well, I guess that looks confusing on the right. I'm trying to think how to explain that. So there's a difference if I had a resistor here. If I had a resistor here, and then a resistor off this side to ground, then it would be a non-inverting amplifier. But because it's still a wire just right back to the input, that's going to be a voltage follower. Let's see, how do I describe this one? So in this case, the input is actually on this other side. So this is what I consider my input here. All right, let's do another one. Oops. Hopefully you can see that that is a comparator. Like there's no feedback on that one, so that would be the comparator. Let's do this one up here. So this op amp here. Okay, I can see where some of you are thinking that it has two inputs in here. So capacitors, what happened with capacitors? And you would do this also in any other circuitry. If it's been sitting there a long time, what happens to them? They're what?
All for a long time, it's open.
They're going to be open, correct? So these basically open up after you've been sitting there a while. And in a little bit, we're going to talk about what does a capacitor do to a circuit when you're looking at it after it's sat there for a little while. And what it does is it changes what frequencies it passes through the circuitry. So in this case, when we're looking at this though, we basically want to open it up and look at it once it's been stable. And with those open, there's really no connection from here to really anything else. And so this would not be an input. It's just kind of a floating wire in there. And so this is going to actually be like at a virtual ground. And so your input comes from here. And so this would be into the negative side, so inverting would be the correct answer here.
Professor,
Yeah.
does the capacitor completely discharge and that's what makes it open and act like a cut wire? If it's sitting for a long time?
So, so the relationship of a capacitor, I is equals C dV dt. So if you have no change in voltage over time, and that means it's like sat there and it's stable, then it would be open because dV dt would be 0. I goes to 0, so this goes to 0, meaning I goes to 0. And we know that with I equals 0, that looks like an open. So that's where that kind of comes from. We're going to start talking a little bit more today. When we start talking about frequencies, the other way you kind of know that it becomes an open is that when we transform a capacitor or an inductor into the Laplace domain. So what we want to do is, we've only looked at one capacitor and one inductor. What if we have a whole bunch in our circuitry? We don't want to go through the derivation each time and be like, well, this is probably a general solution to that exact one. So instead we want to change it into the Laplace domain, analyze the circuit with this acting as an impedance, and then from there we can have as many capacitors as we want, as many inductors as we want, and it's just we treat that like an impedance in the circuitry. When we start to talk about the frequency part of it, we substitute j omega for s, and when we're at DC, omega is 0. So 1 over 0 looks also like an infinite impedance, which would be an open also. So either way you can look at that. If you just want to look at the characteristic equation, which is the I is equal to C dV dt, or if you start thinking about it as far as acting like an impedance at specific frequencies. Okay. All right. Any more questions about identifying? I think we got all those except for that last one, which is not anything. All right. Any questions? Yes.
Would we have to worry about any thing with the capacitors, or should we study more of the op-amps with capacitors?
No.
Okay.
I'll try and make them straightforward. Or I'll try to make it clear, like treat these as an open if you're going to do it. Okay. Other questions? Okay. Okay, so the next part was individuals wanted me to go over like if you have multi-stage amplifiers, so I thought this was a good one. Okay, so you're going to want to break these down into look at each amplifier by itself first. So I'll call this 1. Let me do a different color. 1, 2, and 3. So looking at 1, find the voltage at, I'll call it VO1. So what is going to be the equation for VO1? So you're going to use the same technique to identify what is this kind of configuration, and then you're going to use that table to determine the actual value that it's giving you for the gain. So he just asked if I'm going to supply the table, so just have it handy, so you put it in a place that will print it out and have it there for yourself, or have it easily accessible on your computer. So I will not supply it for you. So one is inverting and which one? So just at that note, so with that, then this would be gain. Iron mods, which is just leave it in terms of V1. So your equation should be VO1 equals something V1. Okay, so hopefully you've identified that this is inverting. And with inverting, you'll go back to the table and say like, oh, okay, this is my equation minus RF over RS. RF will be the one that's in the feedback over that one. So in this case, matching which resistor is which. And it is this resistor over this one. So it would be minus 6K over 2K times V1, which gives me minus 3V1. So 4V1 looks like that would be a non-inverting, that would be the correct one if it was, the input was, if V1 was grounded here instead, and the source was on this one, that would be a non-inverting one, but it's not, so this one is inverting. Okay, for 2, go ahead and find the voltage at this node, VO2.
Sorry.
All right, looking good. So correct, it is a non-inverting. And the equation for non-inverting is going to be, put this R2, R1. VO2 is 1 plus R2 over R1 times the input, in this case would be V2. So that gives you 5K over 1K and then 6. So this would be 6V2. So then you have to take, those two are then your input into the third op amp. So you treat VO1 and VO2 and then you can substitute in those next. So go ahead and find the value for VO. Yeah. Do you see that though? Why
Yeah.
those signals pathways?
Yeah. Yeah. But when you're inputting, like you are, how do we do that? Like, because we're doing so like we have our posted those are like our 8K and our 2K. But I'm talking about the 2K. How do we like adjust? How do we use the 3K and the 6K? How do those affect? Okay, so it's just if you use your stuff, you don't have those.
So correct that they're coming into the plastic input. It could be also both of them. So that's gonna be like if they want this, it's gonna be one that has more than two. So, and then you know if you wanna put them on, but if it was one small. That would be not Okay, so this one, had a couple different equations. Okay, let's see which one is the correct one. So pathway goes into the plus side, and it's only going into the plus side, so it's not going to be a difference. So with that, it will be a non-inverting summer. The equation for non-inverting summer is V out is going to be equal to this resistor over this one. So I'll call that R2 and R1 again. So 1 plus R2 over R1. And then it's a ratio between these two of each one. So this would be 3 over the total times V, this one I don't remember which one's which. Inverting summer. So RS1, so it's the opposite one. So RS1 over those would be the gain for the opposite one. Okay. So V2 opposite. So in this case, this would be VO2. And then 6 over 9. Sorry, I should have called these. I'll call this RS1 and RS2. So this is RS1 over the combination of both times VO2, and then RS2 over the combination of both, VO1. So this one is going to be 1 plus 8K over 2K times 3K over 9K, VO2, plus 6K over 9K, VO1. So this becomes 5 times 1/3 VO2 did I do that right? 8, 5, yeah. And then this is 2/3 VO1. And then we would substitute those in. So we have VO1 was -3 V1, and sorry, I wrote that in the wrong side, -3 V1, and then VO2 was 6 V2. So this becomes 5 times 6 divided by 3 is 2 V2 minus 2/3 times 3 is 2 V1. And so that becomes 10 V2 minus 10 V1. So that would be correct. So one person got it right. Okay, questions? You guys good with that? Yes, no? Okay. All right, so moving on to the new topic. So do use that unit to practice to be able to do the first order and go through and solve those. I know last time when I asked for which type of problems, these were the 2 that were requested. But do review on your own for the first order. Okay. All right, going back to the rescue robot and also the communication with the swarm of robo-bees. Also thinking about the wireless communication between an implanted pacemaker and external monitoring devices. All of these communications happen with a sending of signals that encapsulate the information, and then you send them through some means. It could be hardwire through an actual wire itself, if you hooked up a physical wire. But the nice thing about these is that they're all done wirelessly. So they're either transmitting to some tower, and then that data goes then to somewhere else, like your cell phone. Or with the RoboBees, they're just right by there, so they're communicating to just a very small distance away. With the pacemaker, that's actually internal, and then you have to transmit all that signal through the body to an external device on the outside. So how this is done is through a signal itself. So we call this the electromagnetic spectrum because it has the whole range of identified, I can't speak today, limits. So this is actually the allocation in the United States for these spectrums. And each one, you can't read these very well, each one has a very specific band of frequency that you can use to transmit. So for medical devices, it's going to use a very small window here of transmission. This is easier to read. So these are typically the ones for industrial, scientific, medical bands. You usually can work in these frequency ranges. So between, for example, 6.765 megahertz to 6.795 megahertz. Very limited range though, right? So one thing we have to do with electronics is format the signal so that it's in that range. And then when we receive the signal back, we have to interpret back that signal. So we want to look at a signal when it is only operating in one of these specific frequency ranges. So we call this system a filter. So we use filters to limit the frequency range so that we can use these for very specific applications. And so we are going to learn about filters. And so there's some concepts that you kind of need to understand before we move right into filters themselves. So when we talk about filtering, we want to understand from a circuit what already is happening with the frequency. So as I mentioned earlier, it's hard to be able to like, okay, I'm going to use the derivative itself, like the dV/dt, and for every capacitor that's in my circuit, I'm going to use that dV/dt. I'm going to get, if I have 5 of them, I'm going to get a 5th order differential equation that is going to be a nightmare to solve. So, taking an easy way, and what that is using either the Laplace transform, which allows us to move from a time domain into a frequency domain. And then we can convert back into time. Now we can analyze any circuit that has 5th order, 6th order, 10th order. It can be an unlimited number of orders. And with this technique, it actually becomes really easy. So instead of differentiation and integration in the frequency domain, it becomes a multiplication and a division. So that becomes so much easier to use. So we use transforms. So we use a Laplace transform to convert from a time domain into the frequency domain, or we use an inverse transform. So an inverse Laplace or inverse Fourier transform to move back into the time domain. So this makes it really nice in that, as I said, in the frequency domain, all we have to do is add, subtract, multiply, divide instead of doing an integration. Well, I guess you have to do an integration to come back into the time, and you have to do an integration to go to the frequency domain. But if we match up our signals well and use tables that are already there for us, or we use a computer, it makes it much nicer for us to transform those signals. So the other thing we need to know is like, well, what happens with a resistor when we transform from time domain into the frequency domain? Nice thing is a resistor stays the same. So a resistor in the time domain remains a resistor in the frequency domain. It doesn't change. So it has its own impedance and it stays. For an inductor, so depending on, S is going to be for the Laplace and omega is going to be for Fourier. So we can use either one of those two. I like S because it's easier to work with. And then if I want the Fourier, I just transform it into j omega and then can do whatever I want. Either transform it back into the time domain. So I tend to like just transform it into S first and then go from there. So once I get into the time domain for an inductor, I treat it like a resistor. So it adds just like a resistance. If I have 2 of them in parallel, they are in the parallel form together. So I can reduce them down and I treat it just like a resistor with the value that's imaginary with the S or j omega. So whichever one I have. Capacitor goes to 1 over CS or 1 over j omega C. Again, I treat just like a resistor. And then our input signals, we can do the same thing. We can pick which one, which if I start with Laplace, I need to, and I transform my signal using Laplace, I need to inverse transform it with the Laplace again. So whichever one I do, I just have to kind of stick with. So the other way that we're going to be able to get some information about a circuit is what we call the transfer function, where our input goes in, we have some function that's now a function of S or a function of j omega, and our output is just going to be H of S times that. So X out is going to equal that, and X out J omega is just going to be that function times the input as a function of frequency. So from this, H of S or H of J omega is just going to be X out over X in of whatever variable we have in there. So if I'm given a circuit, I can find this transfer function. And I do that by getting an equation for the output based on the input. And then I just divide the input. And that resultant equation is called my transfer function. So one of the reasons that I didn't mention yet is that we'll sometimes get noise, or we'll get an effect of some other, so this is called an unshielded cable and then a shielded cable. Sometimes we'll have components that come really close to other components. And this electromagnetic field will actually create errors in that wire and that signal. And so we may get what's called an inductive spike, or we may get something else that causes a spike within our system that I want to filter out that error. So this is another reason to filter signals, is to remove errors. And this is called a parasitic effect, meaning that, of course, I don't want to have this affect another circuit, but in fact it does. So most things are shielded now. But there used to be a lot more spiking that would happen in circuitry. Okay. The next thing that we kind of have to understand is a signal itself. So different kinds of signals. This would be considered, so there's two signals, AC, DC. So DC is a direct current, usually is a fixed voltage, like 5 volts. Minus 15 volts. So usually batteries would be a DC signal, and an AC signal is going to be any sinusoid. Typically, we use sinusoids to represent any signal, and all information can be modeled by a representation of sinusoids. So you can, a voice, for example, your voice actually can be modeled by a summation of a whole bunch of sinusoids. So that kind of goes into the Fourier series, where you can model any signal, arbitrary, non-arbitrary, by a summation of a whole bunch of sinusoids. So we know like sinusoid is a basis that we can then work off. So we're going to always model everything with just a simple sinusoid. And then next period, we will actually like go back into the details of a sinusoid and remember like amplitude and phase, and then talk about leading and lagging more on that one. But this would be an example of an AC circuit or an AC signal where it's just a simple sinusoid. This is an example of where we have a DC and AC signal. So this is where it's shifted by 2 volts. So instead of your sinusoid being right at 0, you now have a shift of 2 volts, and then your sinusoid is oscillating around that 2 volts. So mathematically, we would write that as 2 volts plus the sinusoid. So there's a DC component and an AC component. What about this one? There's 2 sections of it. This one is going to be a fixed one, right? So it's going to be DC or AC. This would be considered DC. And then plus and minus 1 volt. It's not a sinusoid, right? But it's a whole bunch of noise that's kind of in between that range. So we would still consider this an AC signal. So this part would still be an AC signal. So this is very common if you guys have looked on your oscilloscope. When you're measuring things that have a little bit of noise, you see a little bit of fluctuation across there. Sometimes they'll be 60 hertz based on the wall signal. So it's picking up some of that through the benches, and you'll see a little 60 hertz signal in there. Other times it can just be some noise itself, just introduced by different reasons. So it would look more like this, just not, it'd be random. In between kind of a height and a low, a high and a low. All right. Okay, I'm gonna get into, well, okay, so this is an example of, oh yeah, I forgot to take them off this one. Thought I erased these. Anyway, these are some of my notes from 2280. So time domain, sinusoid, frequency domain is going to just have a spike at the frequency itself. So this would be, look like that. It would just have one representation, and it tells you, oh, okay, this only has one signal. All right, so as I mentioned before, when we analyze these circuits, we're going to change these over now to 1 over CS or 1 over j omega c, and then we are going to analyze them from there. So we want to know, to get more information off of this, we are going to build something called a Bode plot. And to start, we would analyze this circuit using the 1 over CS and analyze this. So I am going to try and find the transfer function of this, which is going to be your V output over your V input. So my output node is located here. And so if I can find, well, I could do this several ways. If I find the voltage at VA, I can do a voltage divider. So that would be one way, and then VA, I would have to combine all of these. So 1 over CS So 1 over CS would be added to R2, and then that would be in parallel with R3. So that equivalence would be VI times VI. Plus RI. So that would be one way to find the equation, is to go through all those steps. Another way would be to do what I mentioned before, was that node voltage at VA and VO. So I'm not gonna, I'll leave it as an exercise for you guys to derive these and manipulate these to get down to this end equation. So one thing we need to do is put the H of S in what's called standard form. And the standard form is going to be where you have S times a number, or S plus some number. Or it could be a number S plus a number too. But most of the time we want just S by itself. Whoa. And you'll see in a second why. So those are kind of the what you mathematically have to modify it to get to standard form. So looking at this and getting it down, I have a number times S, and then I can get this into standard form by just dividing the 266.7 nano by taking that out of the parentheses and dividing the 1. Do convince yourself that those are the same expressions. So this would be what I consider standard form. So now I have this VO over VI, or I could say it's H of S. And as I said, we're trying to get what's called this Bode plot. So I substitute S equals J omega, and then I can take the magnitude of that, because now I have my imaginary number in there with J. So if you remember from complex numbers, hopefully back in pre-calc probably, if you have a number A plus BJ, and I take the magnitude of that, do you guys remember what it is?
Square root of a squared plus b squared.
Thank you. A squared plus B squared. Okay. So also imaginary numbers, you can take the magnitude of the top and the magnitude of the quantity below. So I can separate those out to have 133 nano omega J. And then the magnitude of that is just going to be J itself, because I have no real portion of it. And then the magnitude of the bottom part, this will be considered my, I think I called that B. So this would be considered B, and this would be considered A. So I have 1 squared plus 266.7 nano, and then omega squared. So I treat omega as a known number. So with this number, these numbers, I now have a function with just omega and no imaginary in it, and I can graph this. I can put omega is 0.1, I can put omega is 1, I can put omega is 10, and so on, and I get a fixed number for each omega in there. So doing that, I can do this in Excel or somewhere else, and I can plug that in. So at omega equals 0.1, that value came out as 39.95852 in dB. So I'm going to get to dB in a second, but I just want to show you that for each of these values at 0.8 omega, it was plugged into that equation above and then a value. So each one of these, I can then plot it and get a graph like this. We're going to ignore this bottom one. We're going to just do the top one. So ignore my phase ones. We're only going to talk about the magnitude. Okay, so these are in what is called a dB. So a decibel is the dB. And we graph all of our Bode plots in dB, because they show us more information than if we were in a volt per volt. So this was voltage output over voltage input, so it's a volt per volt ratio. So dB is also logarithmic, and it was derived by Alexander Graham Bell. I'll put a video up about a little bit more about the history of it. You guys can get some sense for that. What you need to take away is, like, how do I convert to dB? So to get dB, what you're going to do is take 20 log of the ratio itself, and that converts it to dB. If you're going backwards, you're going to take 10 with the dB value over 20. And this converts to volts per volt. So you'll need to be able to convert back and forth between the two. So get very comfortable with that. Okay. So this example had a different equation, but the same idea. If I have multiple quantities, I can find the magnitude of each of those and multiply them together, which is what was done here. And then I can get this graph. So what this graph tells me is that 38. I have some flat regions in here. And when the regions are flat, oh, sorry, go ahead.
I'll ask it.
Okay. So along the bottom of this graph, this is in omega, which is radians per second. And so for different omega, you have a semi-log graph here. And on the bottom side is going to be in decades. So this will be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then the larger gap gives you 1. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and then this is 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, to 20. Or I mean to 100. Oops, sorry, this was wrong. So this is 10, 20, 30, 40, 50, all the way up to 100, and then this is 200, all the way up to 1,000. So that's your bottom graph. And then on the side, this is in dB. All right, that is all we have time for today. Next time I'm going to show you how to look at the equation and just graph that right away instead of having to go in and plug it into the equation each time. All right, see you guys on Thursday for the exam.